It's time to learn about global extrema. In the last video, we talked about local extrema and how we could find them by looking for points at which the derivative of the function is 0, and looking then at the sign of the derivative just to either side of those points. We also noted that we don't actually need the function to be differentiable at all points, which we can see with this graph. If we look at the intervals on which the function is differentiable, we can still look at the sign of the derivative to tell us whether there's a local max or min. Now we're going to talk about global extrema, which means that we actually do care that the values are the largest or smallest that the function achieves anywhere on its domain. The global maximum of a function f is the value of f at a point x equals a, such that f of x is less than or equal to f of a for every x in the domain of f. Note that we no longer restrict our attention to a small interval around a. We need to consider how f behaves on its entire domain. Likewise, the global minimum of f is the value of f at a point x equals a, such that f of x is greater than or equal to f of a for every x in the domain of f. Collectively, these are called global extrema. The word absolute is a common alternative to global. Let's look at an example. This function has a global maximum at this peak and a global minimum here. It's not a problem that the global minimum is achieved in two places. It's still the smallest value that f achieves, and that's what really matters. But what if we look at the graph of a cubic polynomial instead, or a quadratic? The cubic has a local max and min, but neither is global. The quadratic has a global minimum, but no max. In fact, it doesn't even have a local max. I should say here that we're considering these graphs on the entire real line, so they keep going in the indicated directions. Worse than either of these is this graph, which not only has no global extrema, but has infinitely many local extrema. If you tried looking for global extrema at the places where there's a horizontal tangent line, you'd be quickly frustrated if you didn't see a pattern. The point is that finding global extrema can be very hard. There's a special case, though, where things tend to be easier, and that's when you're dealing with a function restricted to a closed and bounded interval. Now we can see that there's both a global maximum and a global minimum. In fact, this is always true as long as f is continuous. If f is a continuous function on the closed interval from a to b, then f has a global maximum and a global minimum on that interval. We can no longer only look for places where the derivative is 0 or doesn't exist, though, since we might also have a max or min at one of the endpoints of the interval. Here, for example, the global maximum occurs where there's a horizontal tangent line, but the global minimum occurs in an endpoint. So we have an additional thing to note, namely that the global extrema occur at x values at which f prime is 0 or doesn't exist, such points are called critical points of f, or at the endpoints of the interval ab.